All right. Any questions before we get going? Questions? So several of you elected to turn your test in on Canvas, but any questions before we get going? All right. Again, I realize I'm just trying to be as generous to you as possible. I realize that a lot of the WebAssign assignments aren't aren't due until like the end of November. Okay. With the compressed schedule, I just want to give you as much time as possible. I don't think a lot of, especially the later WebAssign assignments, are hard to get done fairly rapidly. So, I mean, my encouragement to you would be to try to be done by the time we actually do the final, which would be, I think, Monday of finals week. So I would try to get through it all and not delay an additional week to try to get everything done. I don't have to have grades in until like December 15th, which is like almost a month after we're done. But you know, the faster you get that in, the faster we'll be able to get the course in the books. But I don't, what's weird, so everything will be in Canvas, so you'll be able to tell what your grade is, but you won't actually see your grade in Cedar Info until that December 15 date comes. Okay, so sorry about that, but I mean, you'll be able to see it in Canvas well before that, okay? I'll have everything in there. As soon as I have your WebAssign assignments in the books, I should be done well before that December 15th date. Okay? All right. Let's talk about cylindrical coordinates. Well, I'm just gonna review what they are. Remember, the cylindrical coordinates really are just the polar coordinates in disguise. Yes? It's a three-dimensional rendition of that. So R and theta represent the same thing that they did before. You're basically exchanging X and Y for R and theta. And Z is Z. There's no change whatsoever. We went through a few examples and we ended with this little picture of various situations you might run into. So the right circular cylinder, x squared plus y squared equals 9. You simply replace x squared plus y squared with r squared, and you take the square root, and you see that this thing is really just given by r equal to 3. Okay, r equal to 3 is going to sketch out everything at radius 3 away from the origin in the xy plane, and z is free, which is why it smears out that right circular cylinder. Okay, some other things, x squared plus y squared equals 4z. That's a so-called elliptic paraboloid, if you will. Sometimes it's just called a paraboloid. And if you replace x squared plus y squared with r squared, you get the second equation there. Similarly, the third one is a cone, and we actually know this from our work on quadric surfaces. X squared plus y squared equals z squared plus 0. That's a cone. That's where the thing has been stretched to its limit. Remember that? Okay. If you put r squared in there and basically take the square root, you get the equation, or you get the equation r equal to z. How simple is that? Okay. Similarly, you know that x squared plus y squared equals z squared plus 1. That is going to be a hyperboloid of one sheet. Talked about that with quadric surfaces. You replace x squared plus y squared with r squared, and you see that even that equation simplifies. Okay. So cylindrical coordinates are already making life easier in terms of, right, in each one of these cases, you reduce the number of variables by 1. You see? The number of variables is decreasing by 1 every time. Okay. Let's talk about spherical coordinates. Okay. So in the spherical coordinate system, of course, this is a system that's probably going to be optimal in the case where we're considering surfaces of a spherical nature. Okay, that's not always true, but certainly the spheres are easy to describe in the spherical coordinate system, okay? So this first letter kind of looks like a P right here. It's not actually a P, all right? It's rho. It's the Greek letter rho. And the reason you use the Greek letter rho is because it's supposed to remind you of radius again. But you don't use R because what has R already been reserved for? The polar coordinates. Yeah? So R is used up, so we have to dip into another alphabet altogether, namely the Greek alphabet, and we use the Greek version of R, namely rho. Okay? And then you have theta, which I'm telling you, theta is the same as the polar and the cylindrical coordinates. So theta is the same exact thing as it was before. Then you have a new angle. This is the Greek letter phi or phi. I don't know. If you go talk to Dr. Rogers, he'll probably be real sophisticated and use phi or something. I think phi is sort of the unsophisticated way of saying it. So sometimes I just do it just for spite, right? So I'm going to say phi, okay? Phi is the angle made, like if I were to actually put the point on a segment emanating from the origin, okay? Or like a vector emanating from the origin, phi is the angle made between the positive z-axis and that vector, okay? So essentially, it's basically the angle between the point thought of as a vector emanating from the origin and the vector k. Remember the vector k, like 0, 0, 1? It's basically the angle between those two things. So phi is the angle between the positive z-axis and the line segment OP. And you might say, why does it say that phi is always between 0 and pi? Well, because you don't really need to go any further than 180 degrees. Like going from 0 to 180 degrees allows you to describe anything all the way up at the North Pole, all the way down to the South Pole. Do you understand? So you only need 180 degrees to do that, okay? We put the stipulation on here, at least the book does, that phi is positive, or at least non-negative. It could be 0, and that rho is positive, and so is phi. Phi is between 0 and pi. That's not actually necessary for the case of rho. You could also deal with rho just like you did with R, right? If R is negative, we knew what to do, correct? If rho is negative, it just means that instead of going like rho is going to be the distance between the origin and the point. If rho is negative, that means you just flip around to the other side. Do you know what I'm saying? So you could do a similar thing even if rho happens to be negative. And we'll look at this more closely in just a minute. Any questions on that before we move on? So this is really sophisticated. It's like all Greek letters, right? Rho, theta, phi, right? That's how this works. In the cylindrical coordinates, it was r, theta, z. Now it's rho, theta, phi, okay? So that's clever. Now, I will say that spherical coordinates are similar, although not exactly, but they're very similar to locating points on the surface of the Earth using longitude and latitude, okay? I don't know if you know about longitude and latitude. The way I learned it was latitude is always kind of, horizontal circles on the sphere the circles have to be parallel to the equator, yeah? The equator of the surface of the Earth. And then, so that's latitude, okay? Latitude is that way, and it reminds you of a ladder kind of going up. That's how I always remembered it. That's sort of stupid, right? But just telling you, okay, latitude, I always think of like laddered, a laddered collection of circles on the surface of the Earth. Longitude are the vertical ones, okay, that go through the North and South Pole, okay? So here's a little picture. So assuming the Earth is spherical, which I think we could pretty much assume that, okay, at this point, okay? By the way, if you ever want to, last time I was talking about spontaneous human combustion and in the Philadelphia experiment. If you want to, if you want another afternoon of pleasure, you should go read about flat Earth stuff. Okay, that's sort of fun. There's something called the Flat Earth Society today. It's pretty interesting. That's right. It's a Flat Earth Society. There's also something called the geocentric. It's called the Geocentric Society. They believe that the Earth is actually the center of the solar system. Does that make sense? They still sort of believe that. And they make some very sophisticated arguments, okay? I don't know how to refute it. I need to go read more, okay? But I don't think that's true, okay? I mean, I'm just saying, it seems like all of the data seems to point to the sun being the center of the solar system, okay? But look at this picture. Do you see the positive z-axis kind of going up like this? Okay, so there's the positive z-axis. The positive x-axis is going this way, okay? And the positive y-axis is going this way. It's kind of going out the back of the Earth there, the way this is written, okay? So what you do is you basically say, you think of, so this thing right here is called the prime meridian, the thing that's delineated right there. So you kind of put the positive z-axis on the North Pole, you put the positive x-axis going out through the prime meridian. And then you have the equator, of course, yes, which basically the equator lives in the XY plane. You know what I mean? The equator itself kind of lives in the XY plane. And most of the time, it's like this point right here on the surface of the Earth, yeah? So this is like looks like it's, you know, kind of on the East Coast somewhere or something, right? Essentially what you're gonna do is you're going to say, well, how far away from the origin is that? Okay, well, the distance from the origin is gonna be the radius from the center of the Earth out to the surface of the Earth, which I'm telling you is about 4,000 miles. Okay, 4,000 miles, which is why this first member, which is rho, is 4,000, okay? Then what you do is you say, well, okay, how do I measure sort of, okay, how do I measure sort of the angle that this makes, right? So I don't know, I'm gonna go like this. This angle right here, okay? This angle right here, because that's basically theta. Well, theta is positive if you're up here, yes? So theta would have been positive if you would have been up here. But we're going backwards, yes? We're going backwards how far? Well, it says 80 degrees west of the prime meridian, which basically means theta is negative 80 degrees, okay? Which is where this thing comes from right here, okay? So 80 degrees west of the prime meridian means that. And then it says 40 degrees north. That means north of the equator in that direction. But the way that spherical coordinates are measured are down from the positive z-axis. Do you understand? So if we had to go 40 degrees up from the equator, 40 degrees up from the equator, how many degrees did we go down from the positive z-axis? So think about it. How many degrees did we go down from the positive z-axis? If it's 40 degrees up, how many degrees down did we go from the positive z-axis? 50, yeah, 50 degrees. 50 plus 40 is 90, right? 90 degrees would have been from the North Pole all the way down to the equator. Okay, so that right there is 50. Okay, so that's 50 degrees. Okay, which is why you have this third member right here. So that's rho, theta, and phi. Okay, phi. Does that make sense? So it's not like what you do when you report things in longitude and latitude, you say like 80 degrees west. What that means is west of the prime meridian, okay? And then you go 40 degrees north, which means north of the equator, which is the same as 50 degrees down from the North Pole, okay? Does that make sense? Hopefully. Okay, hopefully that kind of makes sense, but we're gonna like see this all kind of fleshed out here in just a minute. So any questions on that? All right, moving on. So here's what's going on in general. Okay, so we have this point P, and it has two coordinates or two ways of expressing it, either rho theta phi or XYZ. Okay, and we want a relationship between XYZ and rho theta phi. Okay, and this is a picture that really makes everything very clear. Okay, so first of all, what should we do? Well, let's first find an equation for Z. Okay, an equation for Z in terms of rho and phi. Okay, so does this picture make sense? Do you kind of see this page swinging out of the Z-axis? And what we're doing is we're saying, okay, if I were to project this thing down here into the XY plane, so this would be X comma Y, then I know how X relates to R and theta, yeah? And then I have to somehow incorporate this new angle measure, phi. And of course, rho's involved also. So by the way, this distance right here is also Z, if you think about it, yeah? Okay. So here's the thing, this distance up here is R also, okay? This is a right triangle, and this is a right triangle, correct? See what I'm saying? So, look, can I write Z in terms of rho and phi? Can I write Z in terms of rho and phi? Yes, I can use some trig. What trig functions can I use? Or what trig function would be most helpful in this case? Cosine, because I have the adjacent side and the hypotenuse, yes? So you know that cosine of phi is equal to adjacent, which is Z over hypotenuse, which is rho, yeah? So I get that Z is equal to rho cosine of phi. That's exciting. Okay. Yeah. Okay, so Z is equal to rho cosine of phi. That's how we would that's how we would, like if somebody gave us something if somebody gave us a point in the spherical coordinates, I could convert, I could actually figure out what Z is immediately by taking rho and phi and plugging into this formula, okay? Now here's another thing I would point out immediately. Don't you see that sine of phi, look, I can write that in terms of R, can't I? Yeah, and R in rho. Sine of phi is going to be R over rho. Do you see? So what does that mean R is equal to? Rho sine of phi. And I'm telling you we're done. Because we already know what X and Y are in terms of R and theta, don't we? Yeah? And we just figured out what R was. Okay? What's X equal to in terms of R and theta? We already did that like back in the day, right? Back in the polar coordinate day and cylindrical coordinate again, right? So what's X equal to in terms of R and theta? X is what? R cosine of theta. But then if you're like, I don't want R anymore, I can replace R with what it is in the spherical coordinates. So I get that X is actually, looks complicated, but it really isn't when all is said and done. X is equal to rho sine phi cosine of theta. Do you see? That's because this right here is just R. Yeah? That's exciting. What about Y? What's Y going to be equal to? Yeah, that's R sine of theta. And so if I do a similar replacement, that's going to be rho sine of phi sine of theta. You see? So those look like complicated, formulas, but they really aren't. Okay, so I have this, right? I can immediately, once I have the spherical coordinates, I can convert to X and Y and Z. And I mean, look, if I really wanted to, I could figure out, you know, this is just for my own personal edification. R is equal to rho sine phi. I could get at that fairly quickly as well. Okay. There are other things in this picture that should be screaming to be understood. So for instance, you know that like z squared plus r squared is equal to what? Rho squared. But what's r squared? X squared plus y squared. So you got z squared plus y squared plus x squared is equal to rho squared, right? That should kind of remind you of the r squared relationship from the polar coordinates. Okay, so if you give me x, y, and z, I can determine rho now, correct? Okay, other things that might be sort of screaming at us from this picture. Well, I'm going to leave it at those 4 things, right? Actually 5 things for right now, but we have a couple of other things that we can get at fairly easily. Any questions on this before we try to summarize what's happening with all these relationships? Any questions? Here's some nice geometry going on here. So here we go. We already found an equation for x, but here are the main equations. Spherical to rectangular, x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho sine or rho cosine of phi. We even had an extra one that we just, you know, tacked on for free. R, what was R? R was rho sine phi, right? So this is R right here, and this is R right here, yeah? Rho squared is equal to x squared plus y squared plus z squared. Tangent of theta, we already know that that's y over x. Know what I mean? Okay, so I could figure out what theta is just based on y and x. I don't even need z at all, okay? And what about, so you know that z is equal to rho cosine of phi, correct? That means that cosine of phi is equal to z over rho. And you might say to yourself, hey, I can get rid of rho. That's the same thing as z over, right? If I think of rho as being positive, then I can literally take the square root of x squared plus y squared plus z squared. Know what I mean? Okay, so it's going to be the square root of x squared plus y squared plus z squared. And then, of course, from that equation, I can just get phi from the arc cosine function. And that works out perfectly because arc cosine always delivers an angle between 0 and pi, doesn't it? Arc sine is between negative pi over 2 and pi over 2. Arc cosine is between 0 and pi. Arc tangent is always between negative pi over 2 and pi over 2, okay? So, so phi is equal to the inverse cosine of z over rho. And we just replaced rho with what it is in terms of x, y, and z. Yeah? Make sense? Okay, we're just doing some trigonometry here. We're just trying to capture everything, okay? All right. So what about spherical to cylindrical? Well, okay, so I know, right, from the previous slide that r was equal to rho sine of phi. Okay, so that's where this equation comes from. Okay, just to make sure that, you know, in the case where r is negative, that this equation still works out. So, and of course, theta is just theta. I mean, what could be easier than that? Yeah. And then z, of course, is rho sine or rho cosine of phi. Okay. What is rho? If somebody hands me the cylindrical coordinates, rho is equal to the square root of x squared plus y squared plus z squared. Then I just replace x squared plus y squared with r squared, correct? You know that x squared plus y squared is equal to r squared, okay? Right, theta is theta. And what about phi? Okay, well, all I do is just replace x squared plus y squared with r squared, correct? Okay, so this is how I can flip back and forth from rectangular to spherical, spherical to rectangular, spherical to cylindrical, cylindrical to spherical, etc. Yeah, it's all mixed together. Okay, questions on that? Spherical coordinates, useful for spheres and cones. That's definitely true. What surface do you get if you hold a variable constant? Think about it. What if I say that rho, remember rho is the distance from the origin. What if I said that rho is 5? What would that sketch out in three-dimensional space? What is the set of points such that rho is equal to 5? What would that be? A sphere of radius 5, centered at the origin, yeah? Okay, so first of all, rho equal to c gives you a sphere. Oops, I accidentally gave away the form on the other two. We already dealt with theta equaling a constant. We did that last time, remember? That just gives us vertical planes through the z-axis. We did all of that last time. Remember we had all those planes kind of slicing through the z-axis. Okay, so theta equal to a constant gives you a vertical plane, a vertical half plane through the z-axis. Okay. What about phi equal to a constant? The set of all points at angle equal to some constant like pi over 4 off the positive z-axis, you're going to get a cone. Yeah, you're going to get a cone. Okay. So spheres, half planes, and cones are the things that you get when you fix each one of the spherical coordinates equal to a constant. Okay. Any questions on that? I think that's kind of cool, but any questions on that? Let's, I'm going to give you a minute to kind of work on this. Convert 3 minus 2, 2 from rectangular to spherical. So in other words, this is x, this is y, and this is z. And I want you to convert this over to rho, theta, phi. Okay? And this guy, this is rho, theta, and phi. And we're wanting you to convert to x, y, z. Okay? So take a couple of minutes and work on that, please. And we'll reconvene. All right. So let me ask you, what octant is that point in? Remember, we kind of start where all x, y, and z are positive. That's the first octant, yes? 3, negative 2, 2. What octant is that? 3? Isn't it 2? Isn't it the second octant? Yeah. So it's like this. So here's x, y, z. Yeah. Octant 1 is this one right here. Yes. Okay. It's this area right here. Okay. Okay. The only thing is y is negative 2 here, yes? So it moves us from octant 1 over to here, yeah? Or hang on. Y is negative 2. Oh, wait, you might be right about this. So hang on. So that's octant 2. Octant 3 is over here. What octant are we in, actually? It's the 4th octant, right? We're over here. Okay, so that was kind of fun, right? So we're over here, yeah? Does that make sense? So x is 3, y is negative 2, z is positive 2, yeah? Okay? So we're over here, okay? Over here in that area. That's octant 4, okay? So what about the conversion to spherical coordinates? How would I get rho? How do I get rho? Yeah, so rho squared is 9 plus 4 plus 4, is it not? Yeah. So rho squared is 17, which means that rho is square root of 17, yeah? Okay. What about theta? How do I get theta? Yeah, so theta is going to be arctangent of y over x, yeah? So negative 2/3, who knows what that is, but we can do it, right? Right, it's just negative, or it's y over x, okay? Now, what about phi? What do I do with that? Yeah, that's right. It's arc cosine of z over rho, right? So arc cosine of z, which is 2 over the square root of 17. It's exciting. Whatever that is, yeah? We can sort those things out, yeah. Well, yeah, there's not much you can do with that, right? Unless you had a calculator, right? But at the very least, this is precise, for sure. You would have to be clear about whether you were reporting these things as angles, as in degrees or in radians. Yeah. Okay. Now it's clear in this second problem that we're dealing with radians, right? Because we're talking about pi and whatnot, correct? So we're dealing with radius or radians in the second problem. So I know that rho is 20. I know that phi is 2 pi over 3. I know that phi is pi over 4. Okay, that's interesting. What octant is that in? The second one, yeah. Okay, so phi equal to 45 degrees, that keeps us above the xy plane, yes? Because phi equal to 90 degrees would be on the xy plane, but we're above the xy plane. Rho is 20, and then theta is 2 pi over 3. So that means it doesn't quite, right? It only goes 2/3 of the way to 180 degrees, which puts us basically in the place where x is negative and y is positive, correct? So we're in the second octant, yes. Okay, so what's x going to be? Well, it's going to be rho sine phi cosine of theta. Okay, so everything gets involved here. So it's going to be 20 sine of phi. What's the sine of pi over 4? Radical 2 over 2. Okay, that's good. And what is the cosine of 2 pi over 3? That's interesting. So what's the cosine of 2 pi over 3? You guys remember? What's the cosine of pi over 3? Oh, right. So the cosine of pi over 3 is 1/2. So the cosine of 2 pi over 3 would be negative 1/2. Yes. Okay. Okay. So what this is going to end up being here is negative 5 square root of 2. So there's the x coordinate. Okay. The y coordinate is rho sine phi sine of theta. Okay, which is 20 square root of 2 over 2. What is the sine of 2 pi over 3? Well, that's going to be the same as the sine of pi over 3, which is square root of 3 over 2. Okay. So it's going to be 5 times the square root of 6. Okay, square root of 2 times square root of 3 is the square root of 6. And finally, z is rho cosine of phi. It's exciting. Okay. So it's going to be 20 times, okay, what is the cosine of phi? Well, phi is just pi over 4 for crying out loud, right? Cosine and sine are the same at 45 degrees. So times square root of 2 over 2. So this would be 10 square root of 2, right? So the x coordinate is negative, the y coordinate is positive, and the z coordinate is positive. So yes, you are in octant number 2 in this particular case. Yeah? Any questions on that? It's kind of fun. All right. Identify the types of surfaces. Okay, so what is x squared plus y squared plus z squared equals 9? What kind of surface is that? That's a sphere of radius 3 centered where? 0, 0, 0. Okay? So to convert this to spherical coordinates, that's easy. It's just rho equals what? 3. That's it. Okay, what about this guy right here? What kind of a surface is letter B? What is that? What kind of a surface is that? Look, if I subtracted 3z over, I can complete the square for z, and I would get a sphere of a particular radius. Do you know what I'm saying? Okay, what that radius is precisely might not be totally clear right now. I promise you, like if you subtract, for instance, if I were to subtract this over, you would actually add 3 over 2 squared to both sides, yes? So you'd actually add 9/4 to that side, and you would add 9/4 to that side. So that, I am telling you, this is a sphere of radius equal to 3/2, centered where? Centered at 0, 0, 0, 0, 3/2. And I'm telling you, that's what you would end up getting if you kind of completed the square, did your due diligence there, okay? Well, what is this, though, in the spherical coordinates? Well, the left-hand side, x squared plus y squared plus z squared, that just collapses to something simple, namely what? X squared plus y squared plus z squared is rho squared. This would be rho squared equals 3z. Well, z is just rho cosine of phi. What can I cancel from both sides? Rho. So I get rho equals 3 cosine of phi. Okay, that ought to remind you of the polar coordinates. Remember when we had, like, if we had r equal to 3 cosine of theta, that would have been a circle, yes? Here we have rho equal to 3 cosine of phi, and you'll have the 3-dimensional analog of a circle, namely a sphere of a particular radius, of radius 3/2 actually in this case, okay? Okay, what about this last guy? What about this last guy here? What do we do? Well, what is that? I mean, we kind of know what that is. I'm telling you, it's a cone, okay? That thing is a cone. So, So this guy right here is r squared, isn't it? Yeah? And so this would be 0.5 or a half equals z squared over r squared, yes? Okay. It seems like we've seen z over r somewhere before, haven't we? Where have we seen that before? Let's look at this picture over here. Z over r, okay? This is r right here. Z over r, okay? Z over r. What can we do there? What's that? Hang on, say it again. Okay, so z, okay, so z equals, well, okay, so hang on a second. What trig function would involve both z and r? Tangent, okay? So tangent of phi, right? You know that tangent of phi is equal to what? R over z, correct? Okay. So in other words, let's go back over here. Let's go back to where we were before, which is right here. Okay, so tangent of phi is equal to r over z. So let's kind of flip this thing on its head. This means this is the same thing as 2 equaling what? R squared over z squared. So this means that 2 is equal to what? What's r squared over z squared? That's just tangent squared. Tangent squared of phi, okay? And that's maybe not the only way that we could express this. Can you think of other ways that we could express this? So you could just say, look, I want the set of all phi, or I want the set of all points such that tangent of phi for that point is equal to 2. I'm telling you, you're going to get, or the tangent squared is equal to 2. You could take the square root of both sides, by the way. And you could express this as tangent of phi is equal to the square root of 2, for instance, yes? And that would be one way to sort of express that. And you could say phi is equal to the arctangent of the square root of 2, and that would be perfectly all right, yeah? We already knew that cones were basically phi equal to some kind of constant, and that's precisely what's going on here. Phi in this case is just the arctangent of the square root of 2, okay? There might be other ways that you could express this using some other trig functions, but this one's probably just fine, okay? So phi is equal to, in this case, phi is equal to arctangent of the square root of 2, right? So phi is equal to that particular constant. That's how you would express that thing, yeah? Any questions on that? Okay, so we had a sphere, a cone, okay? I'm going to just leave these in here and let you kind of think them through. This is going from cylindrical to spherical, okay? It's not too hard to kind of make that happen. And then from spherical to cylindrical, okay? Remember, that should be fairly straightforward because you know what x and y are in terms of the cylindrical coordinates. There's r cosine theta and r cosine theta and r sine of theta. And then you basically replace r with rho sine of phi, and you're done, yeah? And you can go back to the cylindrical coordinates also. But also, I put a couple of problems from the end of the section here at the end that you can kind of think about. Like there are certain solids that you can sketch just by thinking about what happens if I let theta go between 0 and pi over 2, r go between 0 and 2, and z go between 0 and 4. What would that first one be, by the way? That would be a good place to kind of hang our hat on. What would that first thing be? If theta is between 0 and pi over 2, if theta is between 0 and pi over 2, we're talking about this stuff right here, correct? Yeah? What about z between 0 and 4? Well, that just means that z is trapped here between 0 and 4, yeah? And then r between 0 and 2. Well, okay, so that would just mean I would kind of sketch this guy, this circle, and it's everything inside of here, yeah? So I think what we would get here is this solid. Yeah? You see what I'm saying? Yeah? You just get that kind of cylindrical, that part, 1/4 of like a cylinder in this particular case. Looks like we've kind of sliced off 1/4 of this particular cylinder. It's 1/4 of a cylinder of height 4 and radius 2. Yeah? That's what that first one would actually be. So that's the sort of thing that you do on these last 4 right here. It's kind of fun to think through those sorts of things. Okay? I'm going to leave it at that and call it a day. Again, if you ever test, put it up here. Be great. What's that?